Okay, so this week our problem set is titled Model Eye and Ametropia. All right, so Model Eye, we spoke about Model Eyes in the past, and when we're talking about Model Eye here, we're talking about the reduced schematic eye. All right, and the reduced schematic eye is going to have a single source of dioptric power. Okay, that power is going to have no thickness, so we're going to call it an SSRS, a single spherical refractive surface, and we're going to say that it has a power of 60 diopters. Okay. Now, if this model eye is emetropic, in other words, the refractive error is equal to 0, I would want parallel light coming in. In other words, the U would be equal to 0. All right, because I would have an object out here, and that object will be placed at optical infinity, something greater than 20 feet or 6 millimeters. All right, and if that was the case, that parallel light would hit this converging lens, and it would form a focal point, and that focal point, if that gentleman was emetropic, would have to be at the plane of their retina. Okay. All right, and if that was true, we could figure out what the distance was between here and here. And in the model eye we're talking about, the inside of this eye is filled with a homogeneous indice of refraction, which is going to be that of water, so 133. All right, and so what I want is that power to be equal to indice of refraction divided by, this is the axial length. Okay, remember, the dioptric power is the juxtaposition of the two indices of refraction divided by its radius of curvature. So in other words, indice of refraction on the top and linear value on the bottom. So there is my indice of refraction on top, there's my linear value on the bottom. And if I solve for the x, that comes out to be 22.22 millimeters, and that is now the axial length for an emetropic eye. This is the dioptric power for an emetropic eye. That is a scenario we talked about in previous lectures, and that is the scenario you're going to use for all of these problems. So an emetropic eye is going to have a corneal power of 60 and an axial length of 22.22 millimeters. Okay. All right, that is easy enough. Therefore, I can now say that a refractive error, so something that's not going to be 0, is now going to be the difference between this corneal power and this axial length. All right, so if they are not equal to each other, I will have some sort of refractive error. So that comes up with this thing that says the refractive error is the difference between the power that we have and the power that we need. What does that mean? This could be the power of the cornea, okay? And then this could be, this is a dioptric power, this would be the indice of refraction, and then this would be the axial length, okay? Cornea, all right? Cornea in quotes, because it's not really a cornea, it's just this SRS. Okay, I'm just equating it into what it would be in the eye. All right, and this would allow you to determine what the refractive error is. If the refractive error is positive, the eye is too strong, the patient would be myopic. If the refractive error is minus, the eye would be too weak, the patient would be hyperopic. Okay, if it is due to a problem with the power of the cornea, that would be a refractive ametropia. If it had something to do with the axial length, that would be an axial ametropia. All right, so easy enough there. Now, if I know what the refractive error is, I know how I could make them into an emetrope, and I would place some sort of contact lens at the plane of this SSRS. In other words, all the power of the eye is here, so I could put the correction in apposition to it. In other words, it would have a vertex distance of 0, so now it gets to a contact lens. And so refractive error, in the magnitude of the refractive error, would be equal to the magnitude of the prescription of a contact lens, except it would be exactly opposite. All right, so the difference between the refractive error and the prescription for the contact lens, equal magnitude, opposite sign. Easy enough. All right, now that's for contact lenses. All right, now we're going to want to do for spectacle lenses. All right, so now I am going to have some sort of, let's say sake of argument, this guy had a power of 62. That would make him 2 diopters too strong. Let's say his axial length was correct. This axial length was 22.22. All right, so his axial length is fine, but his cornea is 2 diopters too strong. I would therefore fix him with a -2 contact lens at the plane of his cornea. Therefore, his vertex distance would be equal to 0. That is for a contact lens. All right. And here's his eye right here, and there's his contact lens on top of the eye. Now, let's say, sake of argument, I want to put him into a spectacle lens. I want to move it out to here. And whatever, I'm going to make that into a 14 millimeter vertex distance. That's a standard. All right. And so I'm going to move it out into space here. I want to know what the power of his spectacle lens is going to be. All right. It can't be the same. All right. I can't move the -2. If I put the -2 out of here, is that going to be too much or not enough? Well, think about it for a second. All right. So the light is coming from this direction. The light is hitting a negative lens. It's going to cause a divergent wavefront. Right. This is the D. This is the V. The V is going to be a minus value. It's going to be diverging, okay? Because I'm having parallel light coming in this way, the U is going to be 0, which means the focal point of this system is now going to be in front. Right? That makes sense. This guy's myopic. He has a focal point that's in front of his eye. That makes sense. All right. And now I'm going to now move the spectacle lenses out to here. All right. And so this is a diverging wavefront. The magnitude of a diverging wavefront is greater closest to its point of origin and decreases as it propagates away from that point of origin. Therefore, the amount of magnitude of wavefront that this contact lens had to deal with, this was the contact lens, compared to the spectacle lens, is significantly less. So for a myope, their contact lens correction is always less than their spectacle correction. It's that simple. Let's make him into a different scenario. I'm going to make him a 2 diopter hyperope. Okay. Well, that 2 diopter lens, that's a converging lens. That's going to cause a focal point back here. All right. Makes sense. Focal point of a hyperope should be behind the plane of the retina or inside their eye. All right. So going on that side. All right. That's going to have. Now I'm going to take this contact lens and I'm going to put it out in space here. This is his contact lens, this is his spectacle lens, right? And I'm just going to continue this wavefront here. Now, for the converging wavefront, the magnitude is significantly greater here than it is here. So whatever magnitude of wavefront that this contact lens had to deal with, if I move the correction out here, the magnitude of this wavefront is going to be less. Therefore, a contact lens correction of a hyperope is always going to be greater than that of their corresponding spectacle correction. It's that easy. So I know if this was a -2 here, I know this value out here has to be greater than a -2. If this is a +2 here, I know the value out here has to be less than a +2. Right? And when we go through the scenarios, we're actually going to see how the focal distances of the contact lens and the spectacle lens change, and that's how we're going to get our dioptric values. In other words, the focal distance of our contact lens compared to the focal distance of our spectacle lens. And we're going to see how that changes, and then we're going to turn that into a dioptric value. All right. The other way that we're going to do that is using the Gaussian cheat. All right, this is what I showed you in the past, which is going to be the effectivity formula. And we'll get into more of that in detail when we actually get into Gaussian optics. But for now, when we do some of the problems now, we'll just use the Gaussian cheat formula. And then where that formula came from will make sense to you in the future. All right, so when we come back, we'll start to get into the multitude of problems that we have. All right, start in a bit. All right, so we're going to get started on our problems here. And for the problem set, question number 1, they're going to give you 6 scenarios. So these are model eyes with a given power of the lens and then a given axial length, okay? And they want you to determine a couple of different things, a few different things. What is the refractive error? And then they want to keep the power the same as what it is here. And they want you to make the eye either shorter or longer to make the person emetropic. In other words, having a refractive error of 0. They want to keep the axial length the same, and they want to increase the power of the eye, once again, to make that person an emetrope. They want to know what the power of the contact lenses are going to be to correct this person, and then they want you to find out what the power of spectacle lenses are going to be, and they're going to give you 2 different vertex distances, which is going to be 12 millimeters and 18. So there's actually 1, 2, 3, 4, 5, 6. All right, so these are 6 scenarios with 6 individual problems for each, and I'm pretty sure that means we have to do 36 problems, but anyway, that's what it is. So we'll get started. All right, so for the first scenario, you're going to have an individual that has a power of his cornea which is 68 diopters, and is going to have an axial length which is 23 millimeters. And then once again, what this came from is refractive error is the difference between the power that a person has and what a person needs, or the juxtaposition between the power of the eye and the axial length of the eye. If the 2 of those equate, then the refractive error is 0 and the patient is emetropic. All right. Now, given this in an emetropic model eye, the power of the eye should be 60 diopters. That means that the power of this individual's cornea is 8 diopters too strong, which would make him a refractive myope. In this case also, in a emetropic eye, the axial length of an emetropic eye should be 22.22 millimeters. This person's eye is 23 millimeters long, which would make him an axial myope. So this guy has a choice of being an axial myope or a refractive myope, which means the only option this man has is to be a myope. So you know that the refractive error has to be a positive value, something more than 60. All right, something in excess of 60, and that in excess number is going to be the refractive error. So we're going to take the 68 here, take your 1.33, that's your index of refraction of water, divided by the axial length, and this comes out to be 57.83. Take the difference between the 2, and that gives you a plus 10.17. All right, that is this person's refractive error. Plus meaning his eye is too strong. So it's like an emetropic eye that is now wearing a contact lens that is a plus 10.7. So a refractive error of 0 wearing a contact lens of 10 makes this system 10 diopters too strong. How would you fix that person? Well, I'm going to pick a contact lens RX that is equal in magnitude but opposite in sign. So I'm going to take a negative 10.17 lens and plop it on top of that. That's the reason why we're dealing with this model eye. Remember that all the power in this eye is at the plane of where you would think the cornea would be, and it's an SSRS. So refractive error we can treat as contact lenses. Contact lenses we can treat as contact lenses. All right, so I'm going to take this gentleman here that's going to have his refractive error, and he's wearing a contact lens that has a power of minus 1017. Now, in the scenario, they want to make this guy's refractive error 0. They want to make him into an emetrope. They want to keep the power the same, that's 68, but we want to modify the axial length such that he's an emetrope or his refractive error is 0. All right, so we're going to solve for this x value, which is going to be the axial length for emetropia. I'm going to throw this on the other side here, 133 over x. That's going to be equal to the 68, which means the x is going to be 133 divided by the 68, which means the axial length that will give us emetropia is going to be 0.0196, so 19.6 millimeters. So in other words, if this gentleman's eye is 8 diopters too strong, if we want the focal point of that lens to fall at the plane of the retina, we're going to have to shorten the eye. In other words, 19.6 is less than the 22.22. Once again, your answers must make sense. If you got an answer greater than 22.22, you know that that would have been obviously wrong. All right, now in the other scenario, we're going to keep the refractive error the same. We're going to keep the refractive error 0, excuse me. We're going to keep the axial length the same of what it is in the problem, which is 23 millimeters. And then we want to know what you want the power of the cornea is going to be, or the power of the eye to do that. And you've actually already did that math here. This was the 5783. And so the x comes out to be the 133 over the 0.023. All right, so the power of the eye that would give you emetropia with this axial length is going to be 5783. All right, so we've now found that. All right, now what do we have left to do? Well, we have to convert this contact lens into a pair of spectacle lenses. All right, so we're going to take this contact lens and we're going to shoot it out in the space over here, and then we're going to push it out a little bit more. We're going to push it out by the 12 millimeter vertex distance, and then we're going to push it out by the 18 millimeter vertex distance. So in other words, vertex distance from here to here is 12, and the vertex distance from here to here is 18. Now, what do we know before we even start? Well, if this is a contact lens correction of a -10, what should the value of these spectacle corrections be? In other words, it's going to be more or less than 10 diopters. All right, well, I have a minus lens. That minus lens, when I have parallel light entering into it, is going to cause a diverging wavefront. All right, that diverging wavefront is going to have a focal point somewhere in front over here. If this is my contact lens correction, my spectacle lens correction is going to be towards the object or to the left. All right. The magnitude of this divergent wavefront is going to be significantly greater here than it is here, which means to compensate for that same amount of divergence, the value here is going to have to be more than this 1017. This value needs to be more than 1017, and this value here needs to be more than this value here. All right, so before we even start, we want to make sure that we have our math in check. All right, so I'm going to have my original lens over here. That's going to be my 1017. Once again, that's going to create a focal point to its left. All right, that is going to be the far point of that patient's eye. In other words, a myope should have a far point in front of their eye or to the left, the way we drew the picture here. Once again, light's going from left to right. I am now going to put the correction out here in space, and the distance from here to here is going to be my 12 millimeter vertex distance. Now, if this is the focal point of the contacts, the focal point of the specs needs to be in the same spot, which means the focal length of this lens, the spectacle lens, has to fall in the same position here. So in other words, I need to know what the distance is from here to here. That's going to be the focal distance of the contacts, and I need to know what the distance is from here to here. That's going to be the focal distance of my spectacles at a vertex distance of 12 millimeters. All right. To find this guy here, the distance from here to here, the focal distance of my contacts, I'm going to take the inverse of its dioptric power. That's the 1017, and that gives me a 0.098. So the distance between here and here is 0.098. I now need to know what the distance is from here to here. Well, I know that's going to be less than this guy. All right, this guy is going to be less than this guy. How much less? It's going to be that much less. So I'm going to take the 0.98, that's my original focal distance, and I'm going to subtract my vertex distance, which is like 12 millimeters. When I do that, that'll give me the focal distance of my spectacle correction, which is going to be 0.86. I'm going to take that linear value and I'm going to turn it into a dioptric value. So I'll take the 1 over the 0.086. Remember, the 1 is the index of refraction of air. All right, we're not saying that the patient is in a swimming pool, so we're assuming that the spectacle lenses are out in air. All right, you take the inverse of that, and that gives you 1163. Now, we're measuring from here to here against the path of light. So this number has a negative value associated with, means the dioptric power is also going to have a negative value associated with it. And that's going to be at a vertex distance of 12 millimeters. All right, we're going to do the same thing, but we're going to put it out over here even farther, and that's going to be 18 millimeter vertex distance. So I'm going to take my original focal distance, which is 9.8. Now I'm going to subtract not the 12, but the 18. All right, when I do that, I come out with a 0.080. That is the focal distance of my spectacles at a vertex distance of 18. Take the inverse of the 0.80. Once again, that has a negative value associated with it, and that gives me a minus 12.5. And that is at a vertex distance of 18. All right, so we started out with a contact lens that is 10. We have a spectacle lens that's 11.63. That's definitely more than that. And then this guy should be definitely more than this guy over here. All right, so what are they looking for? Well, we wanted to know what the refractive error, we figured what that was. We wanted to know what the contact lens correction, we figured out what that was. We wanted to change the axial length so that we had emetropia. There's your answer there. We wanted to change the power of the eye so that we were at emetropia. That's your answer there. And then we wanted to know the spectacle correction at two different vertex distances. There it is at 12, and there it is at 18. All right, so we've now answered the problems for the first scenario. All right, well, let's move on to the second scenario. All right, and so for the second scenario, I now have, once again, my refractive error. That's going to be the difference between the power of what I have and the power of what I need. Another way of looking at that is that I want the refractive error to be equal to the difference between the power given of the eye, in this case 64 diopters, and its associated axial length, which is our indice of refraction divided by the axial length given to you in the problem, which is 22.22 millimeters. All right, that's a familiar looking number. All right, and so you should actually know what this is at this point, but this would be 64. This is actually going to give you 60. That is the axial length of an emetropic model eye. And so this is going to give you a refractive error of +4. And think about it. This guy should have, if he's an emetrope, should have a power of 60. He's got 4 diopters too much. The axial length is perfect. He is a 4 diopter myope. How are you going to correct that guy with a contact lens? So the Rx of the contact lens is going to be equal but opposite. So a -4 diopter contact lens. All right. Now I'm going to take this guy, excuse me, and we want to make him into an emetrope. So I want his refractive error to be 0. And I'm going to do that. How am I going to do that? I'm going to change the power of his eye, or the power of his cornea. I'm going to keep the axial length the same, which is the given 22.22 millimeters. All right, and so you already know what the answer to this guy should be, 60, right? But we'll just do it anyway. All right, so the x is going to be the 133 divided by the 22.22 millimeters. All right, and that means that the power that's going to give us emetropia for this guy with that axial length is going to be 60 diopters. All right, easy enough. Didn't have to do the math for that. Could have figured that out on your own, but it works out either way. All right. And I also want him to be an emetrope. I'm going to keep the power of his eye the same, but now I'm going to alter his axial length to make him an emetrope. All right. And so what do I need to do this? If he's 64, do I need to make this eye longer, or do I need to make it shorter? Well, that's too much power. That's going to cause, it's going to make him a 4 diopter myope, right? That means the image is going to form and focus in front of his retina. So I want to bring the retina to the image. I'm going to need to make the eye shorter. The answer has to be less than this value here, 22.22. All right, that's going to be our x value there. All right, so I'm going to have my 1.33 divided by the x is equal to 64, and the x is going to be the 133 divided by the 64. When I do the math for that, the axial length that's going to give me emetropia works out to be 0.0201, so 20.1 millimeters, and 20 millimeters is definitely less than 22 millimeters. All right, so the answer makes sense. All right, so once again, I have an eye this is an emmetropic eye. This is actually a 4 diopter myope eye, so I'm going to put a 4 diopter plus contact lens on to indicate his refractive error. And to repair him, I'm going to put an additional, correct his refractive error, I'm going to put an additional contact lens on that's a -4. All right, so I'm just going to say that this is this guy here. He's wearing his, excuse me, he's wearing his, it should have been a negative lens here. All right, he's wearing his -4 contact lens, and now you want to fit him with spectacles, and the spectacles are going to be out in space here, the vertex distance of 12, and then out in space here, which is going to have a vertex distance of 18, from here to here, and from here to here. All right, now, is the contact lens correction going to be more than less 4? All right, once again, I have a negative lens. That negative lens is going to create a diverging wavefront. All right. I'm placing, if this is the contacts and this is the specs, excuse me, I am going to be moving the specs towards the point of origin of the wavefront. The magnitude of the wavefront is going to be significantly greater here than it is here. Therefore, the power of the spectacles has to be greater than 4. We know that's what the answer is, and so in case we come up with an answer that doesn't follow that rule, we know we made a mistake. Okay. And so, let's see, we got here, I got a contact lens here. It has a value of -4. That's going to create a focal point in front. This is the focal point of the eye right here. Myope has a focal point in front of them. And the value of that is going to be 1/4, or 25 centimeters. So the distance between here and here is 25 centimeters. All right, now I want to put spectacles here. And in the first scenario, the spectacles are going to be 12 millimeter vertex, distance from here to here. So I'm sliding this correction to the left against the path of light. And then, but for these spectacles to work, they have to create a focal point that is coincident with the focal point of the contacts. All right, so I need to know the distance from here to here. That is the focal length of my new spectacle lens. To find that, I'm going to have this guy here, the 25 centimeters, less the 12 millimeters. All right, so I'm going to subtract that off of there. And that gives me 0.238. So from here to here, this is 238, from here to here. That now becomes the focal distance of my spectacle lens, 238. When I'm doing the measurements, I'm going from here to here. I'm going against the path of light. Therefore, this is a minus sign. Do the math, this comes out to be 4.20. That's a minus, and that is at a vertex distance of 12 millimeters. 420 is greater than 4. All right. And so I'm going to do the same thing for my 18 millimeter vertex distance. So I'm going to subtract that, 18. That gives me a 0.232. Take the inverse of the minus 0.232, and that gives me a minus 431. And that's at a vertex distance of 18 millimeters. All right, so once again, we've determined that this guy has a refractive error of +4. We're going to fix him with a contact lens correction of -4. To make this guy into an emmetrope, keeping his axial length the same, we would make the power of his eye 60 diopters. If we wanted to keep the power of his eye at 64, we would have to shorten his eye to 20.1 millimeters. All right? And then if we wanted to put him not in contacts but in spectacles at a vertex distance of 12, that would be 4.20, and at 18 that would be 4.31. All right, now just coming back, we're dealing with a refractive error of 4 diopters. All right, this is the magic number of 4, and so you'll notice when you go from contacts to specs or from specs to contacts, you're now going to have the magical quarter diopter difference between the two. Remember that a quote-unquote normal vertex distance, what your phoropter or your refractor is calibrated for, is going, or the vast majority of them are going to be 14 millimeters for a vertex distance. Your spectacle frames, the vast majority of spectacle frames are going to be designed for an average person worn at a 14 millimeter vertex distance. And you'll notice that at 12, which is under 14, it's just under a quarter diopter, and at 18, more than 14, it's just over a quarter diopter. All right, so that's where the magical 4 is. If the prescription was less than 4, the difference would have been less than a quarter diopter. So when you physically wrote the prescription, because you write in quarter diopter steps, it may be the same, but the power is not the same. In other words, they are never the same. Always keep that in the back of your mind. If you change the vertex distance, the power must be altered or the prescription is wrong. Depending on the perception of the patient, that'll be a problem for you, or that won't be a problem for you. All right, and so that is for the second scenario. We're going to do the third scenario here. Once again, we're going to deal with our refractive error is a combination of the power that the patient has minus the power of what they need. And in the third scenario, you're given that the eye has a power of 58 diopters and that it has an axial length of 0.021 diopters. All right, now what do we got here? Well, this guy's eye should have a power of 60 diopters. He's 58. He's 2 diopters too shy, which is going to make him a refractive hyperope. He should, as an emmetrope, have an axial length of 22.22 millimeters. He has an axial length of 21, which means his eye is also too short. He's got an eye that's too weak. That makes him a refractive hyperope. He's got an eye that's too short. That makes him into an axial hyperope. This poor guy has no chance other than to be a horrible hyperope. All right, now we need to determine how hyperopic he is. All right, 58, do the math on this. This comes out to be 63.33. This number is bigger than this number, so now we have a negative value, right? And so that's going to be 533. And so this guy's refractive error is 5.33 diopters too weak. That's what the minus sign means. All right. Now, if you want to fix him in some fashion, all right, the contact lens prescription, right, is going to be equal but opposite to that. So that's going to be the 533, but it's going to be a plus. All right, so here is an emmetropic eye. This guy, the 5 diopter hyperope, is like an emmetrope wearing a minus 533 lens. I'm going to fix him by putting on a plus 533 contact lenses. That way these two guys cancel out and he's back to emmetropia. All right. Now we're going to try and fix this guy in some fashion. We want to make him into an emmetrope, and we want to do that by changing the power of his eye. So that's going to be my variable, but I'm going to keep the axial length the same. All right, so 0.021. Once again, this is too short, so he's going to be an axial hyperope, which means that this value here has to be more than 60. So when I do my math, this value here has to be a value greater than 60. If not, then you made a math error, okay? So x is equal to 133 over 0.021. And so the power of this guy's eye to make him emmetropic is going to be 6333. Right, 6333, and 63 is definitely larger than 60, and so we're good to go there. All right, we got half a shot. All right, we're going to keep him as an emmetrope. I'm going to keep him as his weak 58 diopter eye, but now what do we have to do? We have to make his eye longer to make him into in other words, this is too weak. It's going to cause the light to come to a focus farther back than normal. So I want to stretch his eye in some fashion. I want to know how much I need to stretch his eye. So we know that this value has to be longer than an emmetropic eye. So the value here needs to be more than 22.22 millimeters. All right, and so I'm going to take the 133 over my x, and that's going to be equal to the 58. And so my x is going to be the 133 over the 58. And so the axial length that's going to give me emmetropia for this guy is going to come out to be 0.229. All right, so 22.9 as opposed to 22.2. So the eye is definitely longer. All right, what are you noticing here? Which one is going to be more of an issue? In other words, creating refractive error. The power of the cornea being off or the axial length being off here. All right. So you'll notice it's 22.22. This is like 7 1/100. So 7/10, less than 7/10 of a millimeter will cause 2 diopters worth of refractive error at the plane of the cornea. So it's obvious that axial length is going to be more significant in creating refractive error than actually having a cornea that is too steep or too long. All right, and when you progress in this program and we start talking about progressive myopia and things like it, you'll understand that the cornea really isn't changing in people. It's their axial length is actually becoming longer. But bear that in mind. You can also use that rule of thumb to figure out what these relative answers should be, to figure out whether a person is going to be a relative hyperope or myope, depending on the juxtaposition of either the power or the axial length. All right, but getting back to the problem, I'm going to have an eye here, and this gentleman is wearing now a plus contact lens. This is his ametropic eye, and he's wearing a plus 5.33 contact lens, and we want to now fit him with spectacle lenses, and these spectacle lenses are going to be out in space here at a vertex distance of 12 and then a vertex distance of 18 millimeters. So from here to here and here to here. All right, so now this is a plus lens. It's going to create a converging wavefront, all right, and I'm moving it farther out in space here in this direction, all right, which means that this wavefront is going to be stronger. The magnitude of wavefront is going to be stronger here than it is here, okay? Which means as you slide this out in space, these spectacle values should be less in magnitude than the contact lens value. So in other words, the answer for these spectacles has to be less than the 533. All right, I'm going to stick with my original lens here. That was my plus 533. It's a converging lens. It's going to cause a focal point that's out here. Once again, a hyperope. Their focal point, or the far point of their eye, is going to be behind the plane of the retina, okay, to the right. All right, just double check and make sure you have your pictures correct. I'm now going to take the spectacle lens and put it out here. I'm taking this power and I'm now sticking it out here in space. For this spectacle lens to work, that focal point, that power of that lens has to equate, in other words, form the focal point in the same spot as the contact lens do. All right, so I need to know the distance between here and here, and I need to know the distance between here and here. I know this, I'm moving it out 12 millimeters, that's from here to here, and I need to know the distance from here to here. How am I going to find that? I'm going to take the inverse of my 533, and that's going to give me 188. So the distance between here and here is 0.188 from here to here, which means the focal distance of this lens here has to be from here to here in order to have that focal point fall in the same spot. All right, so that's going to be my 0.188, and I'm going to have to add my 12 millimeter vertex distance. That gives me a 0, that gives me a 0, that gives me a 2. So 20 centimeter focal distance. I'm going to take the inverse of that value, and that's going to give me a plus 5 lens. All right, once again, I'm measuring from here to here with the path of light. That gives me a positive there. That means there's a positive there, and that's at a vertex distance of 12 millimeters. 5 is less than 533. That makes sense. So this is out here, this is a 5. All right, now I'm going to move this guy out even further, and the distance here, the vertex distance from here to here, is now going to be our 18 millimeters, and that's from here to here. So I'm going to take my original focal length, the 188, but now I'm going to add the 18 instead of the 12, and that is 6, and that's 0, and that's a 2. All right, so the focal distance here is 0.206. Once again, it has a positive sign associated with it, which gives me a positive value there. Do the math, and that's a 485, right? The denominator here is greater than it is here, so the answer here must be less than the answer here. and that is the spectacles at 18. All right, 533, 5 is less than 533, 485 is less than 5, so it follows our rule. Everything must follow the rules. All right, so to sum up, our refractive error for this guy is given as his minus 533. The associated contact lens is the plus 533. To make this dude emetropic, keeping the axial length the same, we would have to increase the power of his eye to 63.33. Keeping him at a hyperopic 58 diopter cornea, we would have to stretch his eye to an axial length of 22.9 millimeters. If we're going to fit him for contacts, it would be fit him not with contacts but with spectacle lenses. It would be 5 diopters at a vertex distance of 12 millimeters and 4.85 at a vertex distance of 18. Once again, we're above the magic magnitude of 4, and so the difference between the contacts and the specs are definitely greater than a quarter of a diopter. Okay, so we're halfway through the first set of problems. All right, and we'll do the second 3 problems when we come back. Okay, so we're back again, and we're doing the first set of problems, but now we're doing the last 3 set. All right, so for the 1, 2, 3, the fourth scenario. All right, once again, we're dealing with refractive error. That's the difference between what the patient has and what the patient needs. And so in this scenario, you're given a corneal value of 62 diopters, and you're given a axial length which is 19 millimeters. All right, so this guy, if he's an emetrope, he should have a power of 60, has a power of 62, and that makes him a 2 diopter myope. So that makes him a refractive myope. He has an axial length that is 19 millimeters, okay, and he should have an axial length of 22 and some change. So his eye is significantly short. All right, so this would make him an axial hyperope. Now we got a choice. He could be a refractive myope or an axial hyperope, and we'll take a guess. Which one do you think? Well, let's say I'm 2 diopters off here, but I'm at least 3 millimeters off here. Given the 2, I think the axial length is going to win, but we'll do the math just to double check. All right, 62 diopters here. Do the math on this. This comes out to 70 diopters, which means this gentleman is a hideous 8 diopter hyperope. So once again, pound for pound, comparing a diopter to a millimeter, the axial length is what's going to push your system. All right, and so to fix this gentleman, this is going to be his refractive error. To fix him, I'm going to put a contact lens on the surface of his schematic eye, so to speak, and that's going to have a value of +8. So I'm going to have an emetropic eye. This gentleman, I'm going to make him into what he is, the 8 diopter myope, by putting a 8 diopter minus contact lens, and I'm going to fix him by putting on an additional 8 diopter plus lens. +8 minus 8, 0. That will make him emetropic. All right, getting back to the scenario, I want to make him emetropic, so he has a refractive error of 0, and I want to change the power of his eye. That's going to be my variable, but I'm going to keep his very short axial length in check, 19 millimeters here. I want to figure out what that is. All right, so that is going to be the 133 divided by the 0.019, and you already did that math over there. And that's going to be, so the power to make him emetropic, he would need to have a 70 diopter eye. He would need to be 10 diopters too strong in the power of his cornea to compensate for his a little more than 3 millimeter axial length. So 10 divided by 3, you got a little more than a 3-to-1 ratio there. Once again, trying to give you some rules of thumb so you can follow and have an idea whether your answers that you're coming up with are making any sense. All right, and this is going to help you in the clinic also once you actually start seeing people. Now, people are not going to have model eyes, obviously, but the rules of the trends are going to follow. In other words, you know, optics is optics. It doesn't matter whether it's in some sort of microscope or some sort of simple optical system or an organic system like an eye. It's going to obey the same rules of physics. All right, so we're going to see what sort of axial length to compensate for his original power, which is the 62. So I'm going to have the 133, the bag filled with water, and I want to figure out what the axial length to make him emetropic. So it's going to be the 133 over the x is equal to 62. And so my x is going to be the 133 divided by the 62. And so the axial length that will make him emetropic is going to be 21.45 millimeters. All right, 62, that makes him a 2 diopter myope. All right, which means that the focal point of this cornea is going to be in front of an emetropic 22 millimeter eye, which means that it has to be shorter. We have to take that emetropic eye and make it a little bit shorter. And we're shortening up by a little more than a half a millimeter. Okay, half a millimeter here compensates for 2 diopters there. That's approximately a 1:4 ratio. So, right? So we're between this 1:3, 1:4 ratio between dioptric power and axial length, diopter per millimeter. All right, now we're going to put this guy in spectacles rather than his contacts. All right, so he is now wearing his 8 diopter plus contact lens, and I want to take that power and put it out in the space here. So these are going to be where his specs are, and the first scenario is going to be the 12 diopter, or not 12 diopter, 12 millimeter vertex distance, and then the second scenario is going to bring it out even farther to an 18 millimeter vertex distance. All right, well, we have a lens here that's going to be a positive lens. It's going to cause a focal point on this side, and I am now moving the spectacles out this way. All right, so I'm going to extend that cone, that wavefront out that way. Going to be significantly more power here than here, and so to compensate for the same amount of power, his spectacle magnitude has to be less than his contact lens magnitude. So the answers that we get for the power of his spectacles must be less than a +8. All right, so we're going to do that. All right, so I'm going to have his original contact lens here, which is a +8. That's going to create a focal point on this side. Once again, for a hyperope, the focal point is behind the retina or to the right, all right, or inside their skull, whatever scenario you want to call that. I want to know what that focal length of that 8 diopter lens is. I'm going to take the inverse of the 8 diopters, and that gives me 0.125. So 0.125 meters from here to here. Now I'm going to put spectacles out here. These are where my specs are going to be again. And the first one is going to have a vertex distance of 12 millimeters from here to here. Well, from here to here. Now, if those specs work, to bring the focal point of the spectacle lens has to be coincident with the focal point of the contact lens, all right? Which means the focal length of the spectacles have to be from here to here, which means I'm going to take that original focal length, 1.25, and add my new vertex distance, which is my 12 millimeters. That's a 7, that's a 3, that's a 1. That is now the focal length of my new spectacle lens. All right, I'm measuring from here to here. That's going to have a plus sign associated with it. Do the math for that, and that gives you 7.30 diopters, and that's going to be at a vertex distance of 12 millimeters. Okay, once again, we said it had to be less. 7.3 less than 8. All right, now we're going to do the same thing out here for our 18 millimeter vertex distance. So the distance between here and here is going to be 18. All right, so we need to know the distance between here and here. This is the 0.137. All right, so I'm going to take the 125, and now I'm going to add in my 18 millimeter vertex distance, and that gives me 143. That's what this guy is here, 143, just to complete our picture. I'm going to take the inverse of my 0.143. Once again, it's going to have a positive value associated with it, and that gives me a 699, not quite 7 diopters. And that's going to be at a vertex distance of 18. All right, so we have 8, 7.3 is less than 8, 699 is less than 7.3. Follows our pattern. The power should be less as we move out. And once again, it's not going to be a linear change of power. Vergence is a nonlinear function. The difference between the two is going to decrease the farther we move out. The magnitude the same, but going to decrease a bit. All right, so not a linear change. All right, so to answer the problems, the refractive error of this gentleman is a -8. His contact lens correction is going to be a +8. Change the power of his eye to make it emetropic, be a 70 diopter cornea. Change the axial length of his eye to make him emetropic. That's going to give him 21.45 millimeters of axial length. Put him in glasses at a vertex distance of 12, that would be 730, and at a vertex distance of 18, that would be 699. Okay, and so that is the fourth scenario. All right, the fifth scenario. Ta-ta! All right, so once again, refractive error is the difference between what we have and what we need. And so in this scenario, we're given an eye that now has a corneal power of 59 and an axial length of 24 millimeters. Ooh, okay, what do you think about that? All right, so this guy is 59, he should be 60. That leaves him a diopter too short, so he should be a refractive hyperope from this perspective. This one here, his eye should be 22 and some change, and it's actually 24. He's 2 millimeters, not quite 2 millimeters, too long. All right, so I have a juxtaposition, so this would make him an axial myope. So I have now, I have 2 millimeters here or 1 diopter here. Which one do you think is going to win? All right, 2-to-1 ratio. I think the axial length is going to win. But anyway, let's double check. So 59 here. Do the math. That's a minus. Do the math here, and that gives you a 55.42. All right. And so even though he's hyperopic here, that myopic axial length is still going to leave him with at least 3.5 diopters of myopia. That is now his refractive error. I want to know what his contact lens Rx is. That's going to be equal but opposite. And there you go there. All right, easy enough. So now I got this guy here. His eye, it's an emetropic eye, model eye. His eye is too strong. To equate that, I'm going to put on a +358. To fix that, I'm going to put on a -358 contact lens over top, and then he magically becomes an emetrope. All right, now, to make him an emetrope, I want to know how I can change the power of his cornea while keeping his axial length the same. So I'm going to keep this at the 24 millimeters. All right, so the X is going to be equal to the 133 over the 024. You already did the math over here. And so the power of the eye to make him emetropic is going to be 55.42 plus, which would make him, a little less than a 5 diopter hyperope, right? He should be 60, so 4 and some change. Let's just say, make it easy, make it 5 diopters. All right, so he would have to be 5 diopters too weak to compensate for his 2 millimeters of axial length. All right, makes sense. Now, once again, I'm going to make him emetropic. We're going to keep the power of his original cornea the same. That's the 59. All right, but we want to change the length of his eye to make him emetropic. Well, he's 59. He's hyperopic, which means his eye is too weak, which means the focal point of that lens is going to fall behind his retina, which means we want to make this eye longer. So the answer has to be greater than 22.22. All right, I'm going to take the 133 over the X. That's going to be equal to my 59. So the X is going to be the 153 divided by the 59. Do the math on that. The axial length that'll make him emetropic is 0.02254. 22.22 is emetropic, so 3/100, those 3/10 of a millimeter, okay, is going to compensate for 1 diopter of refractive error. 3/10, 1 diopter, 3-to-1 ratio. Okay, everything is following. All right, keep this all in the back of your mind as you eventually get in the clinic and you have an idea of how axial ametropia and refractive ametropia are going to affect each other. All right, here's our fellow here. I'm going to fix him by putting on a minus 3.58 contact lens, and we want to put him in specs. So we want to take this power and move it out into space. So this is where our specs are going to be, and the first vertex distance is going to be 12 millimeters, and the second vertex distance from here to here is going to be 18 millimeters. All right, well, what do we know? All right, well, this is a negative lens. It's going to create a divergent wavefront, which means when I move the lens this way, I'm going closer to its point of origin. The magnitude that the spectacle lens has to deal with is greater than that of the context. Therefore, I know that both of these spectacle lens magnitudes have to be greater than the 358. And whatever this is going to be greater than 358. This guy has to be even greater than this guy. All right, easy enough. All right, so now here is our original lens. That's the minus 358. It's going to create a focal point that is in front, right? Myope should have a focal point in front. I need to know the distance, that focal length of this 358 dioptric value. So I'm going to take the inverse of the 358, and that gives me 0.279. So that is the distance from here to here. I'm now going to put a pair of glasses here, and I want those glasses to be at a 12 millimeter vertex distance, so from here to here. Now, if these glasses are going to work, they need to also form a focal point that is coincident to the contacts. Therefore, the focal length of the spectacle lens has to be from here to here, which means I need to take this guy and subtract this guy. So I'm taking the 279 and I'm going to subtract the 12 millimeter vertex distance. That's going to give me 267. That is now the focal length of the spectacle lens at a vertex distance of 12 millimeters. Take the inverse of that to 0.267. Once again, I'm measuring from here to here against the path of light. That gives me a negative sign associated with that, and that gives me a 375. And then again, that's at the 12 millimeter vertex distance. We said it had to be less than the, it had to be more than the 358, and so 375 is going to be more than 358. All right, I'm going to do it again over here. I'm going to take the 279, and then I have my focal distance, which is 018. I'm going to subtract the two of those guys, and that's going to be 261. I'm going to take the inverse of the 261 here. That's going to have the minus sign associated with it, and that's going to give me a 383. All right, it's even farther out. It's closer to its magnitude, so it has to be stronger, and so the 383 is greater than the 375. All right, so it's all following the rules that we know it should. All right, so to sum up on this guy's refractive error is the 358. I'm going to fix him with a minus 358 contact lens. I can also make him emetropic, keeping his axial length the same, but significantly weakening the power of his cornea. Or I can take his 24 millimeter eye and shorten it, keeping the magnitude of the cornea the same. If I want to put him in specs, it would be a minus 375 at 12 millimeter vertex distance and a 383 at 18 millimeters. Okay, once again, I'm dealing with not less, less than 4. All right, but you'll notice that it's not quite a quarter diopter, maybe a quarter diopter, not quite a quarter diopter difference. We're dealing with a 14 millimeter vertex distance, all right? But once you get up into that 4 range, you're definitely going to have a prescription. In other words, more than a quarter of a diopter difference between the two. But once again, it doesn't matter what the magnitude, they are never the same, okay? Never. All right, so that is the second scenario, all right, and then we're going to have our third, which is actually the 6th out of this group, which is going to be the final one. Thank the creator for that one. All right, so now in this guy's a little bit odd. Once again, we're going to have refractive error is equal to the power that we have minus the power that we need, all right, and in this case, you're told that he has a 74 diopter cornea, and he has an axial length that is 18 millimeters. All right, Let's just take a look at this fellow for a second. All right, he should have a cornea, if he's emetropic, that has a power of 60. So he is 14 diopters too strong. That makes him hideously refractive myope. Okay. Now, we also have an axial length that is 18 millimeters, which should be 22.22. So it also makes him 4 millimeters too short. All right, now, so that makes him a hideously axial hyperope. So I have a refractive myopia and axial hyperopia. Which one is going to win out of that? Well, let's say I'm just going to round it off, and we have a 4 millimeter too short, but then I have 14 diopters. All right, so let's use our rule of thumb. Take the 4, times it by the 3, that gives me 12, and that's darn close to the 14. I don't know who's going to win here, but it's probably going to break close to even. All right, if you do the math, it's 74 here. This guy turns out to be a 73.89, and I'll tell you what, that's about as close to a wash as you can get. That's 11/10 of a diopter. All right, that's his refractive error. All right, that makes him very slightly myopic. All right, if you wanted to fix him, his contact lens RX, excuse me, would be, I'm sorry, that makes him just slightly myopic, and to fix him, I would put on a minus contact lens of 0.11 diopters. All right, so we're not going to do the math on this one because the values are going to be very close. All right, but once again, what you're going to use this guy for is you're going to know this is going to be 4 and some change, and this is 14, and so you know it's going to be pretty close. In this case, the 14 beat out to 12. That's where you had your little bit of myopia here. All right, so that is all of the problems. So that is 1, 2, 3, 4, 5, 6 times 1, 2, 3, 4, 5, 6. That was 36 problems we did for the first one. Wow. All right, so when we come back, we'll do the second scenario. And the second scenario is going from contact lenses to spectacle lenses. And we'll do that when we come back.